Hey, can you hear me okay?
Great. Okay, so thank you so much to everybody for coming, and thank you to Steve for that warm introduction. Thank you to both Jeff and Jay for setting this up on a short time scale. I'm really excited to be here. I'm actually in Austin as a part of a number of different events. I was visiting the University of Austin, the University of Texas at Austin this morning, talking to some of the faculty there about different science programs that we're doing. We're also bringing a huge public outreach event to the South by Southwest Festival coming up on the weekend. And I'm going to talk about that a little bit towards the end of the talk, and I hope certainly everybody here, especially the kids, get a chance to come to that event because we're going to have some really cool stuff to give away and some really cool things to show you guys. Being an astronomer at the Space Telescope Science Institute is probably the coolest job that somebody can have in the whole world. It is for me, at least. Not only do I get to tackle some of the biggest questions that face our knowledge about the universe, but I get to be involved in building really, really big telescopes. The telescope that I'm going to tell you about today, the James Webb Space Telescope, is a telescope that's about the size of a tennis court. Okay? And we're going to launch this telescope 1 million miles from Earth to observe the universe with a power that we've never had before in astronomy. And one of the remarkable things about doing that is that you design these telescopes to answer questions that you can't address with the technology that you have today. So you have to design this technology and you answer those questions through those observations. But more importantly, when you look at the universe using a tool that you've never had before, you end up unveiling new mysteries about the universe. And so some of the biggest rewards that will come to us from this telescope will answer questions that we don't even know how to ask right now. And that's really exciting to see that whole process shape out. So let me start today with a picture of Galileo showing the Doge of Venice his telescope. Okay? And so the Doge of Venice was the chief magistrate of Venice. He was the most senior elected official at the time. And it doesn't take an astronomer to look at this picture and realize that the Doge himself is probably not an astronomer. For one, he's not pointing the thing up. Right? And then two, there's still light outside. Right? So it turns out that Galileo was actually using the Doge here as a funding agency. He was trying to convince the Doge that this tool that he was inspired by could be used to spy on enemy ships. Okay? And he could get the Doge excited about this kind of work, excited about this kind of research and this kind of tool. But Galileo, of course, wanted to take that tool and point it to the stars, point it to the sky. And when Galileo did that, he completely transformed our understanding of the universe and our understanding of our place in the universe. One of the first objects that Galileo looked at was the planet Jupiter. Jupiter is the biggest planet in our solar system. And when he looked at it, he saw the moons of Jupiter. And he realized that the moons of Jupiter were actually going around Jupiter. And Galileo inferred from that if the moons of Jupiter are going around Jupiter, then the Earth can't be the center of the solar system. Right? The Earth can't be the center of the universe. Right? And the reason for that is that it's the smaller objects that are going around the more massive object. And so in our solar system, the biggest, most massive object is the sun. Right? The sun is kind of the heart of our solar system. It's what generates all of the heat, all of the energy that we take for granted every day. It's the reason Texas is so warm. Right? And so this is a real movie of the sun. The sun rotates, stars rotate, just like planets. And this is a picture showing structure on the sun over the course of several days. And from the sun, we have a number of planets within our solar system. And so when Galileo looked at those planets, he started putting together a picture of what the makeup of our solar system is and how some of these planets are related to one another, and it inspired the scientific revolution. So at this point, I'm sure the kids are already bored. I have 2 twin 4-year-old daughters, and my kids would be asking right now, Dada, can you get to the time machine part? And so this is interesting. So can astronomers really be time travelers, and can we really build time machines? The answer is yes. Okay? And if we can, though, you have to ask yourself, if I'm really from this era, right? If I can time travel, then I might be from the future. And in fact, if we built time machines, then I might be back in this generation, talking to you right now, but other civilizations might have also built time machines. So I could very well be a space alien coming to Earth to talk to you right now if I'm really time traveling. So let's talk about this a little bit. So how does this work? So here's a picture of our solar system that I took from my spaceship as I came to Earth. And this shows the sun, and it shows all of the planets in the solar system. So I want to explain how astronomers can time travel, I need to introduce a couple of simple concepts. So we're going to do a little bit of mathematics right now first. Okay? So we're going to look at distances of the planets from the sun. So let's start with Earth. So Earth, our planet, is located about 90 million miles from the sun. Okay? 90 million miles. Okay? What about the planet Saturn? Saturn is 1 billion miles. That means it's almost 10 times further from the Earth than the sun. These are huge distances that we're not used to thinking about. What about our friend Pluto over here in the outer solar system? Pluto is 40 billion miles from the sun. I'm sorry, the top is cut off a little bit here. So let's do a little bit of math. So the sun is 90 million miles from the Earth. It turns out that everything in the universe travels with a certain speed. Everything has a certain speed. Just like when we're traveling from one city to another city in our car, we travel at a certain speed. But everything has a certain speed, even light. Right? So if I take my laser pen and I turn it on, there's a beam that illuminates from here up to the roof, and there's photons that are actually traveling from here to the roof, and those photons are traveling with a certain speed. Okay? When you flick the light switch on in your house, that light is traveling from the roof down to your eyes at a certain speed. That speed has been measured. Okay? That speed is about 11 million miles in 1 minute. That's the speed of light. 11 million miles in 1 minute. So that means after 1 minute, light has gone 11 million miles. After 2 minutes, light goes 22 million miles. After 3 minutes, light goes 33 million miles. Makes sense, right? So if you keep going, if we know that the sun is 90 million miles from the Earth and light travels 11 million miles in 1 minute, that means that it would take light 8 minutes to get from the sun to the Earth. Right? So that's the conclusion. The sun is so far away that light would take 8 minutes to get to us. So could this actually be true? So when I'm puzzled in astronomy sometimes, and I have a question like this that I want to solve but I can't figure out, it's good to ask other astronomers. So I ask, my colleagues, my friends in astronomy. So let me ask 2 of my astronomy friends if this could be true, that light takes 8 minutes to get from the sun to the Earth. So my first astronomy friend is Albert Einstein. Right? Very smart guy, rarely wrong. You can rely on him. So if I asked him, if I said, Albert, does light take 8 minutes to get from the sun to the Earth? He would probably say, yes, yes, indeed, light takes precisely 8.33 minutes to get from the sun to the Earth. Okay? But it's always good to confirm things. All right? So let me ask my second astronomy friend. My second astronomy friend, he used to talk to me a lot, but he changed recently. So it's Darth Vader. Okay, so say I ask Darth Vader, Darth, does light take 8.3 minutes to get from the sun to the Earth? He might say, ha ha, my Death Star destroyed your sun 7.5 minutes ago. So wait, so could Darth Vader be telling the truth? Could Darth Vader actually have destroyed the sun 7.5 minutes ago? He could have. We wouldn't know. Because the light that we're sensing from the sun, the heat that we're sensing from the sun, left the sun's surface 8 minutes ago. That make sense? So what that means, simple concept, even when you look at the sun, one of the closest objects in the universe to the Earth, you're not seeing the sun as it is right now. You're seeing the sun as it was 8 minutes ago. So let's push this a little bit. What about our friend Pluto over here? So it turns out that Pluto is so far away that light takes about 1 hour to go from the sun to Pluto. Okay? But all of these planets are like your neighbors on your street that you live, right? These planets are some of the nearest objects to the Earth in the universe, right? What about the stars, right? We look up at the night sky from our backyards and we see all of these stars. So how long does light take from those stars to get to us? So let's think about the nearest star to the sun, okay? Light takes 4 years to get from the nearest star to the sun. Okay? So this should change the way you look at the night sky. Whenever you look at the night sky from now on, remember that all of that light that you're seeing from stars left the surface of those stars years ago. Okay? So with our eyes, we can see nearby objects, we can see some of the nearby stars in our galaxy, but we can build telescopes to see even further away. Okay? So we can use telescopes as time machines by simply looking at objects that are further away in the universe. And as we look at objects further away, the light has taken that much longer to get to us. So the greatest time machine of all, I would say, is the Hubble Space Telescope. Hubble Space Telescope was launched in 1990. And it orbits the Earth. It orbits the Earth at a distance of about 350 miles. And it takes about 90 minutes to go around the Earth. Okay, so once every 90 minutes for the last 22 years, the Hubble Space Telescope has been orbiting Earth, capturing beautiful pictures of the universe, telling us how the universe operates, and making fantastic new discoveries. Okay? So let's use the Hubble Space Telescope to explain this concept of telescopes as time machines, and also talk about some of the astronomy that we've learned from the Hubble. So let me first start by introducing a cosmic timeline. So this is a cosmic timeline. What I'm going to do right now is I'm going to show you some of the most beautiful pictures that Hubble has captured, and I'm going to talk about how far away those objects are and how long light has taken to get to us from those objects. So for example, if an object is pretty close to us and light has taken, say, 1,000 years to get to us, it's going to be on this end of our timeline. If, on the other hand, the object is so far away that the light has been traveling for millions of years or billions of years to get to us, it's going to be on this end of the timeline. Okay? So the first picture that I want to show is one of my favorite pictures in astronomy. Okay? This is a real picture from the Hubble Space Telescope. This is a picture of a star. Doesn't look like a star, but this is a picture of a star. And this is actually a picture of what happens to stars when they're at the end of their lives. Okay? What happens is all of this gas and dust that was in this star, right at the center, gets expelled from the star. A star begins to lose its equilibrium, and it loses all of these outer layers into its surroundings. And the only thing that's going to be left after this process is done is the faint little remnant where the nuclear reactions were happening, the cinder of stellar evolution. So on our cosmic timeline, a picture like this that you can see from the Hubble Space Telescope is located so far away that this is what this picture looked like a couple thousand years ago. And this is actually interesting because this is one of those phases of stellar evolution that happens rapidly. So this phase of stellar evolution actually changes on the time scale of thousands of years. So if you could look at this image today, it wouldn't even look like this. This is what it looked like 1,000 years ago. Let me show you another image. This is a beautiful picture that Hubble took of a cluster of stars. So the star, like the sun, is located in a region of space that it has no nearby neighbors. But some stars form in a region where there's lots and lots of stars. And so the scale of this image is about the distance between the sun and the nearest few stars to the sun. But in that region, there are thousands of stars. So it's a densely populated region of space. If the Earth was orbiting one of these stars, we would have a different sun rising and setting all the time because the density of stars is so great in these kinds of locations. So this is a star cluster. On our cosmic timeline, this star cluster is located so far away that the light has taken tens of thousands of years to get to us. Okay, my third image is an image of another star. This is an image of a big star, a massive star when it blows up. What do you call a massive star when it blows up? You got it. Supernova. Okay? So this is a real picture that Hubble took of a supernova. So again, all of this gas that you see here was tied up in the center of a small star, of a big star, sorry, at the center of this image. And this happens to stars that are about 10 times more massive than the sun. So one of the interesting things about supernovae is that when the universe originally formed, right, the universe was very simple. It had hydrogen and it had helium, okay? Had a little bit of lithium. Okay? But the universe didn't start with all of the heavy elements that we take for granted. Okay? The plastic, that this laser pen is made out of, the carbon, the skin on your bodies, everything, the oxygen that we breathe, those elements were not created by the universe. The only natural environments that are dense enough, hot enough, that have enough pressure to fuse nuclei together and create those elements are the cores of massive stars. In the cores of massive stars, the temperature can reach tens of millions of degrees, right? Under extreme pressure, and you can fuse together those atoms. And so all of those heavy elements are created inside the core of a supernova, and then when that star blows up, it takes all of that material and it sprays it out into its surroundings. Okay? So imagine this process happened billions of years ago. Then at some later point, a new star, like the sun, forms in some region of space. Well, that new star is already polluted by the material from this supernova. So that means that new star now already has those heavy elements, like oxygen. Okay? And around that new star, a little rock forms, like the Earth. And on that rock, the Earth, life forms, like us. Right? So we are star stuff. Right? We were created in the cores of these big supernova explosions. So on our cosmic timeline, we're looking 50,000 years away here. So the light from this supernova explosion has been traveling to us for 50,000 years. And again, this is a scene that rapidly changes. So this would not look like this today. The gas would have expanded to larger scales. It would be less dense if we could see this today. But all of those objects that I just showed you are right here in our own galaxy. Right? What about other galaxies? So this is a beautiful picture that Hubble took of other galaxies like the Milky Way themselves. Galaxies that themselves contain billions of stars. And so this is one of my favorite Hubble pictures of galaxies because it shows 5 galaxies, right? There's one galaxy here, there's 2 in the middle, there's one over here, and there's one over here. And 4 of these 5 galaxies actually have something to do with one another. They're physically associated with one another in space. They're feeling each other's gravity. These 2 are actually in the process of merging together. Okay? But this galaxy over here has nothing to do with these 4. This galaxy just happens to be along the same sight line. It's like if I'm looking at you guys in the back, I see people in my sight line to you guys. You guys have nothing to do with them, right? It's the same thing. And you can kind of see that because the color of this galaxy is different, right? You can resolve little knots of star formation, little star clusters in this galaxy. You can't resolve those in the more distant galaxies, which just looks like a blend of light. And so this is a beautiful picture of galaxies. On our cosmic timeline, this picture represents light that's been traveling to us for more than 100 million years. Okay? So when astronomers look at these types of scenes, these beautiful galaxies, we're looking back in time. We're looking at the universe as it was 100 million years ago. Okay, so Hubble has transformed our knowledge of the universe. Hubble's made amazing discoveries related to black holes. It's measured the expansion rate of the universe itself. One of my colleagues recently won a Nobel Prize for his work using Hubble on measuring the acceleration of the expansion of the universe. Hubble's revealed new mysteries. It's imaged exoplanets, other planets. It's told us how supernovae work, all sorts of science. One of the beautiful things about the Hubble Space Telescope is because it's located at a distance of 350 miles from Earth, we can service it. And what that means is that astronauts, these heroes, they risk their lives to go up to Hubble and change out its old parts. Okay? And so this is a picture of astronauts taking one of the cameras on the Hubble Space Telescope. Look at the size of this camera compared to the astronaut, taking it out of the telescope and putting in a new camera. And when astronomers do this, they end up really with a new telescope because these new cameras are so much more sensitive than the previous generation cameras. And so we're really excited about this with the Hubble Space Telescope because we now have a new technique to use the Hubble Space Telescope to explore even further than we've done in the past. This is a picture of a cosmic magnifying glass. Okay? So this is a real Hubble Space Telescope picture. And what it shows is, it shows a dense grouping of galaxies in a small region of space. Remember we talked about a star cluster where you have a lot of stars in a tiny region of space? This is similar, but here it's entire galaxies. And it turns out that when you get a lot of mass in a tiny region of space, that mass can actually bend space. Okay? Think of space as a blanket. We're holding the corners of a blanket and we stretch it really tight, and then somebody comes along and drops a little marble on the blanket. That marble will bend the blanket. That's what galaxies do to space. They bend it. So anything that passes through that warp will be affected, even light. And so this galaxy that you see here that has this long extended tail, that's an example of light from a background galaxy that's traveling through this warp in space and is being bent. Okay? This galaxy doesn't really look like this. It's just a normal spiral galaxy behind this cluster, but the light is being bent because of the warp. And so one of the beautiful things about these cosmic magnifying glasses is they can produce these beautiful effects of these warps and these arcs that you see, but they can also magnify objects. So by observing systems like this, we can use the power of the Hubble Space Telescope and its new cameras and combine them with these magnifying glasses to see deeper into the universe than we have in the past. So in our cosmic timeline, with this approach, we can see back billions of years. These are two images that are selected as a part of a new program on the Hubble Space Telescope called Frontier Fields that's going to execute over the next 3 years, that's going to take advantage of these cosmic lenses to push beyond what we've seen before. And I'm really excited to show you this because this is a new program that was created by a group of astronomers who got together and thought about how to push the limits of Hubble even further. And one of the members of that group, a small group of like 10 astronomers out of the 10,000 astronomers that we have in the world, was Dr. Steve Finkelstein. So Steve is helping shape how we're going to use Hubble in the future to see deeper than we ever have in the past. Okay, so Hubble's been great. Hubble's continuing to do fantastic things. A popular question that people ask is, Hubble's been up for 20 years. What's next? Right? What are we going to do next? Well, we have very ambitious plans. So right now, we're building a telescope called the James Webb Space Telescope. And the James Webb Space Telescope will be the successor to the Hubble Space Telescope. And so the James Webb Space Telescope is being built by NASA, but it's a huge project. So it's not just NASA alone. It's NASA teaming up with many countries from the European Space Agency and also with the Canadian Space Agency to put together this amazing telescope. And so what are the scientific challenges for the James Webb Space Telescope? These are questions that have emerged given our views of the universe today and some of the new mysteries that have emerged that we haven't been able to answer. So one of them is to seek the universe's first stars and galaxies. And again, sorry that this is cut off by the projector a little bit here. So to seek the universe's first stars and galaxies. So with the Hubble Space Telescope and with other telescopes, we've been able to see further back in time, but the galaxies that we measure are not the first galaxies that formed. And it's really important to detect those first galaxies because that's when all of the physics of galaxies started. That's when the dark matter halos were created in galaxies. That's when the metals were created. And we want to measure those galaxies. But we need a more powerful telescope. And the James Webb Space Telescope provides us with that. Another challenge is to track the formation and evolution of galaxies through cosmic time. So starting with those first small galaxies that formed in the early universe, to figure out how those galaxies merge with one another, how they build up over time to eventually create the beautiful spiral galaxies that we see today in the nearby universe. So with the James Webb Space Telescope's power, we can see all the way back to the early parts of the universe and stitch together this picture by using it as a cosmic time machine and probing how galaxies change over time. Another one of the science goals for this telescope is to solve the mystery of how stars and planets form. Okay? So when stars and planets form, they're enshrouded by dust, right? And that dust can block visible light from escaping. So it's very hard to see stars and planets in the centers of these dust features. The James Webb Space Telescope will actually use infrared sensitivity to penetrate through this dust and detect those stars and planets. So what we're hoping to do with this telescope is find systems in the nearby galaxy that are like our own solar system, but they're much, much younger. They're newborn solar systems. And finally, one of the main science goals is to measure the chemistry of solar systems, so to probe the composition of objects in solar systems, and to probe the building blocks of life. So I'm going to introduce a technique to you which is going to help us not only find other planets that might be similar to the Earth in terms of their sizes, in terms of their masses, but actually study the composition of those planets' atmospheres and try and find evidence in those atmospheres of, try and find signatures that resonate with our knowledge of what the Earth's atmosphere looks like. Okay, so one of the first things that people ask me is, what the heck is this thing? It doesn't look like a telescope, right? So why does it have this shape? So this is a very distinctive shape for a telescope, and so let me walk through the schematics of why it looks like this. So one of the first things that you see on this telescope is this huge sunshield or sail. And there's actually 5 layers to this sunshield. So remember, this telescope is going to be launched 1 million miles from Earth. Hubble orbits at 350 miles. So this is going to be launched past the moon. Okay? And what the sunshield does is it keeps the top side of the telescope where the mirrors are very cold, and the bottom side is going to be very hot because the bottom side is always pointed towards the sun, the Earth, and the moon. Okay? And the colder that we can make the telescope, the easier it is to detect the faint glow of infrared light. Okay? Because it's basically heat that we're detecting from objects in the universe. So the temperature gradient going across these 5 layers of the sunshield is several hundred degrees. Okay? And so the bottom is going to be the hottest, the next layer is a little bit cooler, the next layer is a little bit cooler, and by the time you get to the top layer, it's going to be a very, very cold system. The primary mirror of the telescope is composed of 18 individual segments. Each of these segments is 1.3 meters across. Okay? 1.3 meters across, and there's 18 of them. So when you combine them all together, the mirror is about 21 feet across. That's the biggest mirror that we've ever launched into space, by far. And the bigger the mirror is, the more light we can collect from the universe, the deeper the picture that we can make. On the back of the mirror is all of the cameras for the telescope. Okay, that's where all the cameras sit. And on the bottom are some of the electronics. The solar panels that provide energy, a momentum flap that helps us point the telescope and move it into different directions so we can look at different objects, as well as the spacecraft, which contains all of the batteries and things like that. Okay? So that's why the telescope is designed this way. One of the remarkable things about the James Webb Space Telescope is that when the astronomers came up with these science questions and what they wanted to actually do with this telescope, a lot of the technologies that were required to satisfy those science goals didn't exist. Right? So as a part of the James Webb Space Telescope, we had to create those technologies. We had to pay for those technologies, develop them, mature them, and then put them on the telescope. And one of the real milestones of this project is that all 10 of these technologies have now been successfully satisfied. They're all done. This was one of the major bottlenecks of the telescope, and we've achieved it. So we're really excited about that. And many of these technologies are actually seeing applications both in astronomy and outside of astronomy. Some of the circuits that were developed for the James Webb Space Telescope are now already on board Hubble Space Telescope in the 2009 servicing mission. Some of the techniques that the James Webb Space Telescope has used for optical sensing has led to new innovations in laser eye surgery. Okay? There are US companies that have patents that have generated tens of millions of dollars based on the JWST technologies. So there's a lot of interesting spin-offs there as well. So let's talk about a couple of these. So I want to start by talking about this huge mirror, which is the biggest mirror that we've created and launched into space. So the mirror story is very interesting. First, building the JWST mirrors takes 7 years. It's a 7-year process. These mirrors, initially the beryllium is mined out of Utah, and then the mirrors have to go through a number of different pit stops all across the US before they end up in their final configured shape. And there's extremely tight tolerances on these mirrors to make sure that they function properly. So for example, here's some engineers inspecting one of the JWST mirror segments after it's already been finished. And in the last step of this process, they actually deposit a thin layer of gold onto the surface of the mirrors because gold reflects infrared light very efficiently. Okay? And so this mirror segment has to be extremely smooth for it to work properly. So this is a map. This is something that we call a surface aberration map. And what this map basically shows is how big the bumps and wiggles are on the surface of this mirror segment. Okay? So this mirror segment stretches 1.3 meters across, and the scale of these surface aberrations is nm, which means nanometers. Okay? So what's a nanometer? So a nanometer is, let's start with a meter. Let's take a meter and let's break it up into 1,000 pieces. Okay, if we take 1 meter and we break it up into 1,000 pieces, we get a millimeter. Okay, a millimeter is about that big. So now if we take that millimeter and we break that up into 1,000 pieces, we get a micrometer. Now if we take that micrometer and we break that up into 1,000 pieces, we get a nanometer. Okay? That's the tolerance of these mirrors. Okay? So what that means is that if you took one of these JWST mirrors that was 1.3 meters across, and you stretched that mirror out so that it was the size of Texas, the biggest bump on its surface would be about 1 centimeter high. Okay? And that's the kind of grinding and polishing and smoothness that we need for these mirrors in order for them to produce the clear, crisp, deep images to solve the science cases that we have. And I'm really happy to report that this process has now been completed on all of the JWST mirrors. Okay? So this is a major milestone of the project. All 18 of the primary mirrors, the secondary mirror, the tertiary mirror, other mirrors that are in the parts of the telescope are all finished. So we're really happy about that. What about this Sunshield? So this Sunshield is about the size of a tennis court. And it's one of the most important parts of the telescope because it keeps all of these optics cold. So let me show you a little movie of some engineers looking at the JWST Sunshield. These are real pictures from Northrop Grumman, who's building a large part of this telescope, testing and inspecting one of the Sunshield membranes. And this is an example of some engineers actually working with the Kapton that's going to protect the telescope, making sure it's going to withstand that huge temperature gradient that we need. And so the temperature gradient on the Sunshield, the cold side of the Sunshield will be about minus 388 degrees. The hot side will be 185 degrees. So it's a huge temperature gradient, and this is one of the reasons that we can take these beautiful images with this telescope that are going to advance new frontiers in astronomy. So we're used to thinking of cameras as the objects that we have on our phones now, or maybe a digital camera that we're using to take pictures. This is what one of the cameras looks like on the James Webb Space Telescope. The physical size of this camera is about a meter by a half a meter. So it's like a big block that's about a meter cubed. And this telescope has this camera has all sorts of moving parts in it, and it has sensitive detectors in it, and it's the reason that we can get this beautiful data from the telescope. So one of the main science goals, as we talked about, is to see further back in time than any telescope has in the past. So this is an example of some of the telescopes that we've had from the ground back in the 1990s. Then we launched the Hubble Space Telescope, and then we serviced the Hubble Space Telescope and put better cameras in it. And every time we do this, we see further back into the universe. Okay, so this is like a cosmic timeline going back in time. But the deepest images that we've collected with the Hubble Space Telescope don't quite get us to see those first stars and galaxies, but the James Webb Space Telescope will. So this is a picture on the top of the deepest infrared image that we've ever taken in astronomy with the Hubble Space Telescope. This is a real image. So I'm showing a small part of the image here, and then I'm centering on a bright galaxy in the image and blowing it up over here. Okay? So this is one of the deepest images that we've seen. And on the bottom, I'm showing a simulated image, a simulation from the James Webb Space Telescope of that same image. So this is what a typical image from the James Webb Space Telescope will look like if you just pointed it at some random part of the sky, some blank part of the sky. And the important thing about this picture is not only do you see all of these knots of star formation and the structure in this bright galaxy, but you pick up a lot of the faint galaxies that are around. And some of these faint galaxies are going to be the universe's first galaxies, and then we can study the light, we can study their colors, and figure out what their detailed properties are. And so on our cosmic timeline, this takes us all the way back to when the universe's first stars and galaxies formed. And so this is how we're hoping to achieve the science goal. And the James Webb Space Telescope needs to do this science. Hubble can't, because Mr. Hubble says that trophies are for people with self-esteem issues. Okay, what about the first stars? Right? What about the first individual stars? So we know very little about the first stars, but we have models. We have predictions of what their properties were. And so what we think is that the first stars were very massive objects. They had masses of maybe even more than 100 times the mass of the sun, that they formed in isolation, that they have very hot temperatures. They can reach temperatures of 100,000 degrees. To put that in perspective, the surface temperature of the sun is 5,000 degrees. Okay? So these stars can be very hot. They generate lots of photons, and they have very short lifetimes. So they only last for a couple million years, which is pretty short for astronomical timescales, and then they blow up. And the latest simulations of these first stars actually suggest that after these stars blow up, they're going to remain very, very bright for a number of days, for more than 100 days, okay, almost a year. And the energy that we detect from those first stars is going to diffuse through the ejecta of the star, and it's going to be primarily the infrared energy that makes it out. And based on some of these simulations, these first stars will reach luminosities that can actually be detected with JWST. So now not only are you talking about finding the first galaxies, but you can actually see the first stars that formed in our universe after the Big Bang as they blow up into these big supernova explosions. And this is very important because it teaches us what the properties were of the basic building blocks of the galaxies themselves. So we're very excited about this. So another one of JWST's cameras, this is the near-infrared spectrograph. This is called NIRSPEC, and this is a real picture of all of the different parts of NIRSPEC and some engineers working on it. NIRSPEC is an instrument that's being provided to NASA by the European Space Agency, one of our partners on the JWST project. And NIRSPEC has many different science goals, and the one that I'm really excited about is the search for life-bearing planets. Okay? So we can use some simple logic to try and infer whether a planet might have life on it. Right? We can say that if that planet is too close to its host star, it's going to be cooking, like the planet Mercury. The side of Mercury that faces the sun is very, very hot. If the planet is too far away, the planet's going to be ice cold. Right? Again, life, at least as we define it, life as we know it, may be unlikely to exist on such a planet. So we have different techniques for studying these planets. Two of the popular techniques that we have are the Doppler method and the transit method. So let me quickly explain these methods. So in the Doppler method, what you're essentially doing is measuring the wobble of a star as a planet goes around it. So even if you can't see the planet, because a planet is too faint, what you can do is you can detect the wobble of the star that the planet's going around. So let me give you an example. Okay? So I'm going to jump. The Earth just moved. Okay? It only moved a little bit, but the Earth moved. Okay? And the reason for that is that when two things are going around one another, they're actually going around a center of mass. It's not just the smaller object that's going around the bigger object. So as the Earth goes around the sun actually moves a little bit. Right? When the Earth is on this side, the sun is on this side of the center of mass. When the Earth gets to this side, the sun moves to the other side. And we can detect that wobble. And by detecting that wobble, we can determine what the mass of the planet is. If the planet's more massive, it's going to create a bigger wobble on its star. The transit method is a little bit different. What the transit method is, when a planet comes in front of a star, it's kind of like me walking in front of this projector. So when I walk in front of this projector, you're seeing less reflected light from the screen because I'm blocking some of it, right? I create a little shadow on top of that star. And so by measuring the timing of that shadow, by measuring how the light from the star gets extinguished a little bit, and for how long it gets extinguished, we can determine the planet's diameter. Okay? So these are two popular methods that we use to study planets. And so with both of these methods, we can calculate the density of the planet, we can infer what the internal composition of the planet is, we can tell if it's a gas giant, if it's an ice giant like Neptune, or if it's a rocky planet like Earth. Okay? So the next step in this technique is to try and measure more details about that planet. So in this transit method, what happens is a planet comes around and it's in front of its star, and then it goes behind its star. So when it's behind its star, it's something that we call a secondary eclipse. Right? We see the thermal radiation and the reflected light from the planet disappear and reappear. But when the planet comes in front of the star, the light that we see from the star is not just extinguished, but it's light that's now passed through the planet's atmosphere. Okay? So imagine you've got a star, you look at that star, and you measure a spectrum. So you analyze the light from that star. Now you do that experiment again when there's a planet in front of that star. Well, the light from the star had to pass through the planet's atmosphere to get to us. So the spectrum from the star has now been influenced by the planet's atmosphere. Okay? So you can dig that signal out, and if you can dig that signal out, you can figure out what atoms and molecules are in the planet's atmosphere. You can study cloud patterns, you can study winds, you can do all types of studies. But so far, this has been impossible to do in real planets that are Earth-like planets, because you need extreme, extreme sensitivity in your telescope to be able to measure such a subtle effect. So what do we hope these planets' atmospheres might look like? Well, the first thing that we can ask ourselves, and this is easy for me to do if I'm really an alien, is to ask myself, what does the spectrum of the Earth look like? Okay? So this is actually a spectrum of the Earth's atmosphere, and it's a spectrum that was obtained from reflected moonlight. Okay? And so what do you see in the Earth? So you see oxygen and ozone in the UV part of the spectrum, in the ultraviolet. So these dips that you see are caused by oxygen in the Earth's atmosphere. You see water vapor in the near infrared part of the spectrum. And you see carbon dioxide and methane in the infrared part of the spectrum. So a full-blown living planet with life on it, its spectrum would look something like this. Okay? So here's a simulation of what the data from the James Webb Space Telescope will look like. This is a real simulation of an Earth-like planet. This is a planet that has about 1.5 times the size of the Earth as it's observed with this near-spec instrument on JWST. And what you see is these deep, deep bands that are caused by those very same molecules. So in astronomy right now, we're continuing to find planets in the nearby galaxy. And with the James Webb Space Telescope, what we're going to start doing is dissecting those planets and trying to figure out which of them might have conditions that are similar to conditions here on Earth. Okay? Okay, so this now brings us to the biggest and most profound question facing all of astronomy today. And I had to answer this question recently because my daughters, who are in preschool, were in their space astronomy month at preschool. Okay, so my daughters know a lot of astronomy, right? They know how, you know, that there's nebulae and they can identify different types of galaxies and things like that. But they came home, and so I thought they would be kind of leading in the class. They're 4 years old, but they came home very, very upset at me. Okay, and this was kind of my daughter's reaction when she came home. Okay, and she's an alien too, of course, right? And so what she asked me is, Dada, why did Miss Jamie say that you kicked out Pluto because you're a scientist? So I want to make it very clear to everybody in the auditorium. Astronomers didn't kick out Pluto, all right? Pluto was always an oddball, okay? We've got all these big gas giants like Jupiter and Saturn in the outer parts of the solar system, right? Pluto was different, okay? Pluto was a small, icy object on a strange kind of inclined orbit. It wasn't very much like these other planets. But as we've built stronger telescopes, we've been able to find other objects that are just like Pluto that are located even further from the sun than Pluto is, okay? Some of these objects have moons, just like Pluto has moons. Some of these objects are as big as Pluto. Some of them are even bigger than Pluto. Okay? And they're all located in the outer solar system. So what we decided to do was give Pluto a new family. Okay? And so we created a new family called dwarf planets, and Pluto is now the head of that new family. Okay? So give astronomers a break about Pluto. All right? Okay. So what's the present status of the James Webb Space Telescope? So the telescope is coming together. You know, it's much like building a car. So say you're building a car, right? The same company that's building the engine is not building the tires, right? So all the different parts of the car are coming together. And right now we're in a state where these pieces that come together are being integrated and assembled into the final observatory configuration, okay? And then what we do is we test those pieces. We make sure that they work as they're intended. So when we launch them into space, we're going to be able to get the science questions answered that we want. Okay, so that's the current status of the project. We're expecting to launch the telescope in October 2018. Okay, So in several more years. Perfect for the kids. So one of the biggest pieces of the James Webb Space Telescope development that's still going to happen is a huge test that happens right here in Texas at the Johnson Space Center. And so this is the biggest thermal vacuum chamber in the world at the Johnson Space Center. Those are full-grown adults right there relative to this chamber. And this is the chamber that initially tested the lunar module, okay, during the Apollo missions. And so what we're actually going to do is we're building, actually we've completed building a helium shroud and a nitrogen shroud around this chamber so we can drop it down to the temperature that the James Webb Space Telescope's actually going to observe at, stick the whole telescope into this chamber, and then test it. And so this is kind of a picture of what that'll look like. Here's the James Webb Space Telescope on the base of this chamber. There's an optical stimulus up here that'll shine lights down onto the mirror and make sure that the measured response to those lights is exactly what we expect, given the efficiency of the telescope. Okay? And so this whole test is going to happen in Houston. It's very, very exciting. So one of the mysteries of this telescope is that this telescope is the size of a tennis court. Okay? It turns out that the biggest rocket that we have has a diameter that's much, much smaller than that. So how are we actually going to launch a telescope that's the size of a tennis court 1 million miles into space? It turns out that our friends at Hasbro have solved this problem for us. So just like Optimus Prime can deploy from one configuration into another, the James Webb Space Telescope will be launched into space in a tight configuration, and then after it gets into space, it'll deploy into its observing configuration. And so here's a picture of the Ariane 5 rocket. It's actually going to be launched also by the European Space Agency. Here's the full rocket. There's the James Webb Space Telescope neatly packed at the top of the rocket. Here's a blow-up of that. You can see it's all crammed together in a very tight configuration. And here's a little movie showing the full deployment sequence of the telescope. So one of the first things that you'll see is a little antenna coming out at the bottom, and that's very important because that antenna allows us to talk to the telescope. Right, so there's the antenna. These two booms come out. These booms carry the Sunshield, the Kapton layers that we talked about, the OTE of the telescope, which is just the primary mirror segments. All of the mirror train gets raised up from the Sunshields. What's happening right now is that there's these booms that are extending out to stretch out the Sunshield material. We need the Sunshield material to be in a perfectly stretched out configuration so it can block out the maximum heat from the sun. Remember that there's 5 layers to the Sunshield, so they all get lifted from one another by different pulleys that are on these booms. When all of them are in their fully open configuration, we have a cold OTE at the top, optical telescope assembly, sorry. And then the secondary mirror comes down, and then these 2 little ears come down, which complete the configuration. So that's the full deployment sequence of the James Webb Space Telescope. This is a process that'll take about 10 days to happen in real time. It's a process that'll start shortly after the telescope is launched, only a couple days after the telescope is launched. Okay, so the reason that we're here is that we're going to be featuring a full-scale tennis court-sized model of the telescope at South by Southwest. And so we're going to be doing this at the Long Center for Performing Arts. So this is downtown. This is where the convention center is. This is going to be at the Long Center. It's completely free. So this is going to be next to the Gaming Expo. It's going to be in a big field. And we're going to have the telescope there. We're also going to have lots of other activities, especially things for kids, different STEM activities, different giveaways. We're going to have, sorry, I have a slide on this. We're going to have talks that we're giving once every hour. Right? Once every hour, we're going to be giving different science presentations. We're going to try for a Guinness World Record for the biggest astronomy lesson that's ever been done. It's on Sunday night. Biggest outdoor astronomy lesson that's ever been done. It's on Sunday night. The folks from Guinness are going to be there. Please try to come, help us out. We're going to be doing Google Hangouts and star parties. So every night, people are going to bring their telescopes around the full-scale model and look at the sky. So you can bring your kids and look through that. We have a new comic book that we've created for all the kids that talks about JWST science in an easy to understand way. We've got a collaboration with Microsoft for this huge 20-foot vis wall that we're going to be doing tours with the Worldwide Telescope, panning around to different parts of the universe in a real virtual environment. So it's going to be just fantastic. So please try and come to this event Friday, Saturday, Sunday, all day. We're going to be there for more than 12 hours a day. So please come and say hi. And then finally, who was James Webb? Right? Very important question. We've got the telescope named after him. So James Webb was the second administrator of NASA. He was administrator of NASA during the 1960s. He was the one that executed President Kennedy's vision to send man to the moon through NASA. He also did a lot of other things. So he oversaw the first manned spaceflight program and the second manned spaceflight program. That was the Mercury and the Gemini programs. He oversaw some of the first planetary exploration programs. And he really instilled a culture at NASA that not only did engineering, that not only did technology, but that included science. And so we owe a huge debt of gratitude to him, and so that's why we've named the telescope after him. Okay, so thank you very much, guys.
I'm sure Jason would be happy to answer questions. I just had a swig of water, and I've never done this before in 84 of these episodes. So I'm going to take the first question.
Sure.
Do you work on any cool stuff? Holy cow, that was just amazing. So what questions do you guys have?
Do you want to use the microphone, please?
Yeah, please, if you wouldn't mind.
Actually, if you have a question, why don't you come up and stand behind the microphones?
So I've kind of a two-part question. The first part was you were talking about a real image from Hubble, and something I teach high school astronomy, and one of the things that I'm always wondering at when I look at astronomy photo of the day or whatever is every picture that's done actually what we would see if we were able to do that, or are they all red, green, blue filter? And how can you look at an image and tell how long the exposure was and what it would look like if you were close enough to it? I mean, what does real color mean in those images?
Okay, so that's a great question. So when we construct these images, when we take the image through a filter. So we can put a red filter on the telescope, and basically that will end up giving us more sensitivity to the cooler objects that are in the image that emit mostly in the red part of the spectrum. If we put a blue filter, we can pick up more efficiently the hotter objects in the picture that we're looking at. So after we collect these multiple images of the same astrophysical scene in different filters, we have to put those images together. And so we put those images together to get a colorful image that shows us the different objects in the image. And so the colors are associated with real physical characteristics in the images.
And then the second part of that was when you were talking about how we can tell density and things like that, how do we get from parallax, Doppler shift, and shadows to actually understanding the density and then inferring those other things? Like, how do you make that leap of telling the shadow so we know the density of a planet?
Okay, so the two different methods that I explained, so there's basic laws to, first of all, the way orbits work, right? So the more massive an object is, the different kind of motion it's going to impart on its host star. So if you have a planet going around a star, if that star is bigger, the planet's going to be moving at a different type of speed, right? So you can infer characteristics of that system just through the orbital mechanics, right? In the transit method, you can look at the length of the eclipse. You often have a lot more information about the star because you often have, like you said, a parallax of the star, which means you know what its distance is. And so when you look at the planet occulting the star, depending on the length of that occultation, you can infer what the size of that planet must be. And so when you start to combine these things together, like the mass and the diameter, well, then you can work out the density, because the density is just the mass over the volume. And so you've got all of the right inputs to get that. If you actually want to study the atmospheric composition in much more detail, then you need to use a transit method where you're directly probing what the signature of that atmosphere is. So let's go to this side of the room.
I just have a request. On the previous slide, there was computer that I wanted to be able to copy down that web address. That's all.
Oh, sure. I'll leave this up. Yeah.
Good question.
I'm curious about the formation of the heavier elements. And I heard kind of three things. One, I've heard it said that the heavier elements are formed in the crucible of a star's core. Another one is that the heavier elements are formed during a supernova, that it's the actual explosion of the supernova that is necessary to create sufficient pressure and heat. And then you also mentioned, as we look back at the earliest formation of galaxies when metals were formed, you kind of added that. Is something about the first galaxies also really important about the generation of the heavier elements, or is this just continuing every time over the billions of years that one forms, explodes, and we get more, and then the next generation, and we get more, and the next generation, and we get more?
Okay, so great question. So let me give that a shot. So first, in terms of creating heavy elements within stars, you're creating the elements in the core of the star where the fusion reactions are happening. And so, you can burn hydrogen, and hydrogen will burn into helium, right? That's how stars generate their energy. That's basically what your E equals mc squared formula is. It tells you how the mass difference between that process will be converted to energy. But if your temperature is hot enough in that core, you can then take that helium and you can fuse that together to get carbon. You can fuse that together to get oxygen. So all of that is happening before the supernova explosion happens. And what you end up getting is kind of a layered structure of the star, kind of like an onion, where the different layers contain different products from those fusion reactions. And then when you blow up the star, you release that material into space. Regarding the second question, absolutely. So when you look at galaxies, right? So remember, when we talk about looking back in time and seeing these galaxies, if we were on one of those galaxies and we looked at our galaxy, it would be the same thing. We would be seeing our galaxy as it was billions of years ago, right? And so we can see objects both nearby and far away that have different chemistries. And so some of the small dwarf galaxies, small tiny galaxies that are orbiting the Milky Way are anemic. Right? They have very few heavy elements. And that tells us that those galaxies must have formed in an epoch when the universe wasn't yet polluted by these heavy elements. So it is a continuous cycle because those galaxies are spread out all over the universe now through the universe's expansion. But we can use their chemistry to infer whether they were the first generation galaxies or not. Let's go to the side.
I'm curious about the momentum flap on the telescope and how that allows you to actually manipulate the scope and its orientation.
So the second Lagrange point is an unstable orbit. So the James Webb Space Telescope actually orbits around a point that's called the Lagrange point, and the orbit around that point is pretty big. It's pretty huge. But still, you can build up momentum on the telescope as it's going in its orbit, depending on exactly what object in the universe it's looking at, what the scheduling is like. And so you can use that momentum flap to dump some of that momentum and relieve some of that stress. But there's also fuel on board the telescope, and there's a little motor in the center of the telescope in the spacecraft. And you can spin that motor to change the torques on the telescope to just keep it at a good configuration. And so the scheduling folks, which work at the Space Telescope Science Institute, have a really hard job of coming up with an optimal schedule that's not going to cause a lot of use of this fuel. You want to try and relieve this momentum through the natural processes in the orbit.
So it's going to be so far away that I'm assuming there won't be any manned repair missions if something, God forbid, happens to it. So how did y'all take that into consideration in making the telescope?
Okay, so that's a great question. So the question is, it's going to be so far away. Sorry, it was a little bit faint. So the question is, it was so far away that you can't service the telescope. So how did you, how did you use that input to design the telescope? So that's a great question. If we put the telescope in a low Earth orbit like Hubble is, the radiation from the Earth itself, the heat and the light from the Earth, would be so strong in the infrared part of the spectrum that we wouldn't be able to do the science. The only way that we can do the science is to put it out into a very cold environment in space. And so that's why we have to put it out so far away. But that does come with the risk that, well, now you can't service the telescope, right? So it sets a more finite lifetime on the telescope, whereas with Hubble, we've been able to replace it, take out the batteries, put new thermal blankets on, put new instruments on. We won't have that latitude with this telescope. But once you make that decision, everything that you do in the chain of development follows that logic. So, for example, on Hubble, the first generation science instruments were relatively simple because we knew that we could go up there and service it. On the James Webb Space Telescope, the instruments are packed with different scientific modes of operation to ensure that it's going to be competitive for many, many years.
So, Jason, we have a question from the internet that kind of follows up on that. The question comes from Bill Cohn, and he asks, what is planned to provide protection of the reflectors from any type of space debris, meteors, etc.?
Okay, so Bill, that's a great question. It depends exactly, where a meteorite might hit the telescope. So, for example, we've got this big 21-foot mirror, and this mirror is created from 18 individual smaller mirrors. And so if a piece of space debris hits one of those mirrors, it probably wouldn't affect us too much because we can control the pitch and the tilt of every mirror individually. So we could take that mirror, even if it breaks, and just point it off into a different direction where it's not going to be impacted by some scattered light, and we'll still have 17 mirrors. We'll lose a little bit of sensitivity, but it wouldn't be a big hit. If a piece of space debris, Bill, hits the sunshield of the telescope and makes a hole in the sunshield, well, then we lose our ability to keep the telescope as cold as we would ideally prefer. And so if that happens, then you lose a little bit of sensitivity. So it really depends on the scale of the bombardment and what damage it does to the specific parts of the telescope. I mean, fortunately, the chances of something like this happening are extremely small. The James Webb Space Telescope is in a huge orbit. It's in a 1,000,000-mile orbit. There's not a lot of space debris floating around that would hit something that's, in this case, as small as the telescope, something that's only the size of a tennis court relative to a 1,000,000-mile orbit. So it's something that we're hoping doesn't happen, but if it does happen, it depends specifically on where it impacts the telescope as to what the science hit would be.
Great.
In the transit method of observing the planets going around a star, how can you tell the scale of the planet? How can you tell if the difference between a large planet up close to the star or a small planet further away? Does that make sense?
You have to deconvolve these things through, through the details of the eclipse. So I can show you after. I can show you some more detailed, ways that you look at the signatures of the eclipse to infer, the different those different impacts. Now there is some degeneracy because it depends on, for example, what the inclination is of the planet around the star. So if the planet's eclipsing the star right around the equator of the star, that's going to produce a big effect. Imagine you have the same planet and the same star, but the planet is orbiting that star at some inclination angle. It's going to cut away less of the starlight. And so it does, depend on things like that. So there is some uncertainty as to what the inclination of the events is.
Yeah, well, some of what I was going to ask, I think, has already been asked and answered. But I wanted to know why you're making it why it's so far away. And my understanding is that to reduce the effects of the heat from the Earth. But if it's at Lagrangian point, then it's at the same distance from the sun, right? So it's not going to change the heat from the sun, right? And why at the Lagrangian point? Is that because it makes an easy place, a stable place for it to orbit at, basically?
Yes, exactly. That's right, yeah. So you're moving it away from Earth so you can get away from the heat from the Earth. You're not really moving it away from the sun, right? Because the sun is like 90 million miles away, and it's orbiting 1,000,000 miles from Earth. So it's effectively the same thing within 1%. But you're putting it at the Lagrange point because you can put it there, leave it there, and it'll just continue orbiting that point forever.
Okay.
This is a real quick one. Are you talking about the Lagrange point of the Earth?
It's the Sun-Earth second Lagrange point, L2.
Is that the one that's leading or trailing the Earth?
It's neither, so I think it's on a line between the Sun, Earth, going out.
Oh, right. Okay. Okay, that makes sense. Thanks.
I think those last two sort of answered my question, so I'm going to ask you my backup question.
Sure. Glad to hear you have a backup question.
Yeah. Well, it was the one that I decided was too stupid. If, say, it gets out, you deploy, and everything unfolds except for the left side of the mirror.
Yeah.
I assume that a shuttle is going to go up or someone's going to go up and fix that before it heads out? Or do you have what's the plan for that?
Absolutely not. There's no shuttle that's going to go up and fix it. So if a part of the mirrors don't deploy for whatever reason, then you're stuck with that. Right?
You have diminished capacity.
You have diminished capacity. And the bigger threat is not necessarily the diminished capacity, but those mirrors will be looking at something. right? And so if they end up reflecting the light from that something into the optical path, then you end up getting some contamination. So you'd really want to know exactly where the mirrors are pointed, and you have telemetry that allows you to measure that. The deployment is surprisingly not one of the more technologically challenging parts of this telescope. The deployment is something where there's a lot of redundancy built into the gear motors and things that are going to deploy the different parts. And there are also parts that have been tested heavily in space.
Mm-hmm.
So we're hoping that that is actually a pretty smooth process.
Okay, thanks.
I hope this question makes sense. So I'm wondering, can you see the path of the Milky Way? And
Can you see the path of the Milky Way?
past?
The path to the Milky Way.
Can you see like its creation or something if you looked in the right place, hypothetically?
Accretion, you said?
Creation?
Creation. So, so the path to the Milky Way. So the Milky Way galaxy is our own galaxy. So when we look at different parts of the Milky Way galaxy, just like when we look at the sun or other nearby stars, the light from those different parts have taken years to get to us. But the scale of the Milky Way is small enough that you can't see the Milky Way itself as it was millions or billions of years ago, right? Because it's not that big. What we can study is galaxies that are like the Milky Way, that are more distant from us, and try and infer how our own galaxy came together based on the processes that shape those galaxies.
What I was wondering is essentially, has the Milky Way moved enough since its creation that we could see a past version of it? But
that you can see past?
A past version of it.
A past version of it. No, I don't think in the context that you're asking, but it is true that the Milky Way galaxy is moving. All galaxies are moving. And it's true that the Milky Way galaxy is actually orbiting another galaxy called Andromeda in the nearby, our local volume of space. And so we can predict where the Milky Way galaxy was and how it's changing over time, but not exactly in the context that I think you're asking.
So you've talked a lot about going up and servicing the Hubble. My understanding is that was they've done the last service mission. Is there any change in that status? And if not, when is it going to be decommissioned? And is there a chance that we could change it, or there's no hope at this point?
That we could, what's the last part?
We could service it again.
Okay, so great question, yeah. So the Hubble Space Telescope was last serviced in May of 2009. And since that time, it's been working fantastically. So all of the instruments, the gyros, the batteries, everything's working great. So we have our fingers crossed that the Hubble will give us many, many more years of successful scientific discovery, and there are no plans to turn it off, while it's functioning great. The Hubble would be, Hubble is a very, very competitive telescope, even for professional astronomers to use. Steve and I know this very well. Out of every, 8 or 9 proposals that professional astronomers submit to use Hubble, one is selected, right? So 80–90% of the time that I apply to use the Hubble Space Telescope, I'm rejected. That's how competitive it is to use Hubble. And so it will maintain that competitive edge over other telescopes, even if parts of the telescope don't work anymore. There's 4 different cameras on Hubble right now. There's 2 spectrographs. There's 2 imagers. There's some redundancy as well. So it'll continue to be remarkably successful, even if certain parts stop working. But right now, everything's working fine. You are absolutely correct that there are no plans to service Hubble again, to give it another new lease on life. So NASA has retired the space shuttle. They're developing a more advanced rocket right now, but there are no plans to service Hubble again. So you're right.
Jason, we have time for one final question. So.
Okay, so sure. Let me just say, I'll stick around after so you guys can come up, okay?
Well, first off, let me say, as a UT alum and as a lay enthusiast, thank you very much for coming out and talking. I really appreciate it a lot. Okay. So I actually had 2 questions. One is a technical question. You talked earlier about line of sight. I've always been curious about telescopes. So these images look all great, but isn't there stuff in between us and what you're looking at? I mean, how does that...
So what you do is normally so when you're constructing these deep fields, if you're looking at one of these, if you're trying to look into the universe at some galaxy, the image that I showed is a tiny, tiny region of space. And so if you looked through the disk of the Milky Way galaxy, you would be enshrouded by foreground stars before you got to your distant galaxies. But a lot of the images that I showed are images intentionally taken in empty regions of space.
The second part of my question is, you said the words dark energy or dark matter earlier. So my question is, will JWST do any work around dark matter or dark energy?
Yeah, both of them. So dark matter and dark energy are two of the biggest puzzles that we have in astronomy right now. Dark matter is matter that we know exists, but that we can't see directly. So for example, let me give you an example. The planets orbit the sun, right? Based on the motions of those planets around the sun, we can measure what the mass of the sun is. And we look at the sun, and we know that the sun is that massive. So that makes sense. But when we look at the motions of stars that are going around the center of the Milky Way galaxy, right near the center of the Milky Way galaxy, we can again look at the motions of those stars and calculate how much mass there must be in the center of the galaxy to give those stars those orbits. And when we look in the center of the galaxy, we don't see anything there. Okay? So that's what dark matter is. Dark matter is matter that we know exists, that we can't directly see. And there's a lot of experiments happening right here on Earth through particle physics to try and find subatomic particles that might be responsible for dark matter. And there's experiments happening in astronomy to find out the prevalence of black holes and other dark objects that just don't emit that much light. So the James Webb Space Telescope will make fundamental contributions in those areas, especially through like those lenses that I showed you. Those lenses are a great way of mapping the total dark matter content within that group of galaxies by analyzing the arcs and the tidal tails of those background galaxies that get lensed. And so the James Webb Space Telescope will be much more powerful than Hubble for that type of work. Similarly with dark energy. Dark energy is a form of energy that's propelling the expansion of the universe. And we can measure that influence of dark energy by studying supernova explosions at different distances and trying to figure out, how much the universe must have expanded between the time that the light left some distant object like a supernova and the time that it reached us. And so again, the James Webb Space Telescope will make fantastic contributions to dark energy as well.
Well, as Jason said, he'll be happy to stick around for a little while and answer any other questions you guys may have. You come up to the front. But for now, let's thank him for a really cool talk.
Thank you.